In section 3.1 we're going to be looking at the definition of the derivative. Now a lot of this will be a review when we are talking about the slopes of tangent lines and rates of change. Basically a derivative is a rate of change, and that we've already talked about that aspect of the definition of a derivative. It's also referred to as the slope of a tangent line. And these are just a couple of the applications that we'll be looking at. And it's also known as the limit of the difference quotient. And we'll define the difference quotient here in a little bit. But for the most part, working with a difference quotient, right now we'll be taking a limit, but pretty soon we'll learn some shortcut rules for the derivatives as well. Now in order to develop the idea of a derivative, let's go ahead and recall a graph that we looked at previously. When we were talking about rates of change, secant lines to tangent lines, etc., we looked at a graph that was probably similar to this one right here. And what we were interested in doing is finding the slope of the tangent line at the point A. So we were interested in finding out the slope of the tangent line of this line at the point A. But the slope of the tangent line we knew had to involve the change in y over the change in x. But when we talk about the change in x, that would be dividing by 0, so I had to have 2 points to help us out here. So when we were working with those 2 points, we decided to work with a secant line. So point P is the point where I'm interested in finding the slope of that tangent line. If I plug a into this function, I get f of a back. And let's go ahead and plug in this point over here, and we're going to call this point x. And when I put x in, I get f of x back over here for my y value. And we'll call this point Q. Now, what we have here connecting these 2 points is a secant line. So here's a secant line, intersects the graph at 2 points. Tangent line skims the curve at 1 point. So what we want to do is, in order to estimate the slope of the tangent line right here at point P, you can estimate it with a secant line. Now the secant line is a pretty good estimate of the slope of the tangent line under certain conditions. First of all, if we're looking at this secant line, it's not very close at all. But if we could take this point Q and move it down this curve and get closer and closer to the point P, we can see that we get a better and better estimate. Let's say at this point, we would get a better estimate of the slope of our tangent line. And as we got closer, it would get to be a better and better estimate. Well, what's happening is Q is moving closer and closer to P. As it turns out, this point X is moving closer and closer to A. And so that's one of the things that we think about when we're trying to determine the slope of that tangent line. What is happening with the points of the secant line as they get closer and closer to each other? So the next thing we want to look at is the slope of the secant line through the point P to Q. Not the point, I should say the line P to Q. So, slope is equal to the change in y over the change in x, rise over run. This is going to be f of x minus f of a. That's my change in my y values, f of x minus f of a, divided by x minus a. So that is my slope of the secant line. Now this value right here, f of x minus f of a over x minus a, this is called the difference quotient. And we're going to write the difference quotient a few different ways, but the idea of a difference quotient is going to be very crucial to our development of the concept of a derivative. Then what we do, of course, is we take this value, this difference, x minus a, and remember x minus a is this difference right here, and we want x to get closer and closer to a, so the difference x minus a will get closer and closer to 0. So we're going to use this arrow to say it approaches 0. Okay, and this basically implies that x approached a, got closer and closer to a. Now, as we're doing this, the point Q gets closer and closer to the point P, which is where we're interested in having the slope of that tangent line. So the slope of the secant line does a very good job of estimating the slope of the tangent line as those points get closer and closer. So the slope of the secant line approaches the slope of the tangent line. And that's pretty cool. And again, we're learning some shortcut rules here too, but for the most part that's what we're looking at. So the slope of the tangent line to the graph of f of x at the point x equal a is given by this notation. This is read f prime of a. This is not to the first power. This mark right here doesn't mean to the first. It's a prime mark that means derivative. F prime of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Now a couple of important things here. When we're talking about this limit of this difference quotient, we need to keep in mind this means our function evaluated at x minus my function evaluated at a over the difference x minus a. I do not plug in a value for x. When I take my limit, I'll approach a particular value as x approaches a, but I don't plug in a value right off the bat. Another thing to keep in mind here is this value, this difference quotient value, will give me the slope of the tangent line at a single point. It doesn't give me a generic slope of the tangent line at anywhere along the x-axis, which is kind of what we really want to start developing here soon, because having the slope of the tangent line at a single point is useful, but would be even more useful is to have a generic slope of the tangent line at any point, and then I can just plug in that value. Let's go ahead and look at another way to write this. Now in our graph that we looked up here, this value between x and a, remember we called this x minus a. So what this definition does is it replaces this distance between x and a with the letter h. And that's how we're going to rewrite that difference quotient. So again, another way to look at this is to let h equal that distance between the points, and we let this distance approach 0. So this implies that h approaches 0. So the alternate form that we can look at here is f prime of a is equal to the limit, not as x approaches a, but as h approaches 0, because that's that difference, of f of x is what we used to use. But if we solve this for x right here, we get x is equal to, add the a across, a plus h. So I have f of a plus h minus f of a all over h. And again, that's just with substituting h in for my differences up here. So this is another way that we can write that difference quotient. Now from your textbook, let's go ahead and look at their definition. The textbook definition shows this difference quotient right here that we just got done talking about, and we'll definitely want to memorize this. So this is one method of finding the derivative of a function at a particular point. This is another way that we can do that, and this is called finding the derivative. These will definitely need to be memorized. And we'll have another one that we'll be working with soon too as well. But for the most part, for this section, that's what we want to be looking at. Now, because of the slope of the tangent line is given by f prime of a, the equation of the tangent line is pretty easy to find as well. So again, f prime of a is the slope of the tangent line at the point A. So remember, to write the equation of a line, I need a point and I need a slope. Well, the point is going to be a f of a. Because I plug a in, I get f of a back out. And the slope is just going to be, letter m represents slope, of course, the first derivative, f prime, evaluated at a. So to write the equation of the line then, I have y minus f of a is equal to f prime at a times x minus a. And again, this value of f prime at a is just equal to the slope of the tangent line at that particular point. So let's go ahead and look at an example here. Real quick, this should look pretty familiar from algebra. This is just an alternate form of the point-slope form of the equation. So let's go ahead and look at an example. And we're going to work this example two different ways. I'd like to find the equation of the tangent line. To the function f of x equals x squared plus 9x at a equal 2. Now this is the same as saying at some value of x equal 2. So don't let the a throw you. They're just using that value of a for the formula. Now again, we're going to use this two different ways. The first way I'm going to do this is I'm going to find this using the definition f prime of a is equal to the limit as x approaches a of f of x minus f of a all over the difference x minus a. And again, this is called the difference quotient. We're using two alternative forms for the difference quotient, and this is just one of them. So if we use that definition, if I want to write the equation of the tangent line, I need two things. So to write the equation of a line, I need two things. And the two things that we need are 1, a point on the line, and 2, the slope of the tangent line. Okay, so let's kind of look at our start here. For the point on our line, I already know the x value is 2. To find the y value, I take the x value of 2 and plug it into here. So my y value is going to be given by 2 squared plus 9 times 2. 9 times 2 is 18 plus 4 is 22. So the point on my line is 222. Now the slope of the tangent line I need to figure out. That's my slope. It's going to be f prime at 2. That will be my slope. So I'll use this point and this slope, put it in the point-slope form of the equation, and that will give me my equation of my tangent line. So let's go ahead and find that f prime of 2. F prime at 2, using that definition from above, is equal to the limit as x approaches a, and again I'm pulling these values from right here, but a is approaching 2, of f of x minus f of a is 2, all over x minus 2. Now, what is f of x? Well, f of x is our original function. So let's go ahead and fill in that part. F of x is equal to x squared plus 9x minus f of 2. F of 2, remember, was 22 from up above, all over x minus 2. Well, if I take this limit right now, I get 0 over 0. 0 over 0 is indeterminate. And of course, indeterminate means to do more work. Well, the more work that I want to do here is probably to factor this. So let's hope that it factors. I think it will factor into a nice little product of binomials. X plus 11, x minus 2, all over x minus 2. The x minus 2's cancel, and I'm left with f prime of 2 is equal to the limit as x approaches 2 of x plus 11. And of course what we can do here is just plug the 2 directly in and I get 13. This is my slope of the tangent line at x equal 2. So that piece of information can come up here. My slope is equal to 13 up here. So taking these two pieces of information, the equation of my tangent line will be given by y minus 22 is equal to m, which is 13, x minus 2. Okay, this is the point-slope form of the equation. If we solve this for y, add the 22 across, I get y equal 13x. If I add the 22 across, negative 26 plus 22 is a minus 4. That's the equation of the tangent line to the graph of y equal x squared plus 9x, okay, at x equal 2.